Suppose we have a function f of x that looks like this. We have x squared if x is not equal to 2 and 7 if x is equal to 2. Here's a graph of that function, and we see that it looks like x squared everywhere except for at x equals 2, where we have a hole here. Normally it would be 4, but instead it's 7. So we have a dot up here at 7. And we can look at a table of values as x approaches 2 from the left. Say we have 1, then we would have 1. 1 squared is 1. 1.5, 2.25, and so on. And you can see that as x gets closer and closer to 2 from the left, the value of the function gets closer and closer to 4. This tells us that the limit as we approach 2 from the left of f of x is 4. And we can do a similar thing from the right. We can look at 3. 3 squared is 9. And 2.5 squared is 6.25. And if we keep going, we get closer and closer to 2 from the right. And again, we see that it approaches 4. So we would say that the limit as x approaches 2 from the right of f of x is 4. And since the limit from the left and the limit from the right both exist and they're both equal, we can say that the limit as x approaches 2 of f of x is 4. And note that f of 2 is 7, but the limit doesn't care about what happens right at 2, it just cares about what happens as we get closer and closer to 2. How can we make this idea a little more precise? So here on the right, I've placed all the information that we had before. And we're looking at the limit as x approaches 2 of f of x equals 4. And we see that as x gets closer and closer, but not equal to 2. So we're looking on the graph here, here's 2. We're looking as x gets closer and closer to 2, either from the left or from the right. Then we see that f of x, that's on this axis here, gets closer and closer to 4. Think about it, as x gets closer and closer to 2, f of x gets closer and closer to 4. Okay, so that's the idea that we want to try and capture mathematically. Well, we're talking about closer and closer. We're talking about distance. And the distance between x and 2 we can represent as the absolute value of x minus 2. So think about this. Here's a number line, and we have 2 right here. Okay, there's 2. And we want to look at, say, how about the distance between 4 and 2? Well, the distance between 4 and 2, that would be 2 units. And 4 minus 2, absolute value, yeah, that's 2. How about 7 and 2? Okay, so 7 is over here. That would be 1, 2, 3, 4, 5 units, the distance between 2 and 7. And so the absolute value of 7 minus 2, notice we could also do the absolute value of 2 minus 7. The order doesn't really matter here. That gives us 5. How about the distance between negative 1 and 2? So negative 1 is over here. We have 1, 2, 3 units. Negative 1 minus 2, absolute valued, is 3. So you see in general that the distance between any number x and 2 is just the absolute value of x minus 2. Similarly, we see that the distance between f of x and 4 is the absolute value of f of x minus 4. And so the basic idea is we want to get f of x as close as we would like to 4. In other words, the distance between f of x and 4, we would like that to be as close as possible, or as close as we would prefer. In other words, if I say I would like the value to be within 0.01 of 4, we should be able to do that by picking a value of x down here that would work. So what's a way to figure this out? Well, how about if we say that we want the distance between f of x and 4 to be less than epsilon. So this little thing here, epsilon, which is going to be a positive number, is a Greek letter, and it just means like a small amount. So I want the distance between f of x and 4, this is f of x and the value of the limit 4, to be less than some number epsilon, some tiny little number epsilon. Okay, so how do we make f of x close to 4? Well, that involves something on the x-axis. We want to make x close to but not equal to the value 2. The closer that x gets to 2, the closer f of x gets to 4. So in this case, I want the distance between x and 2 to be less than, we'll say, another number, delta. This is another Greek letter. It's another positive number. And if I let the distance between x and 2 be less than some small amount, then that should allow for the distance between f of x and 4 to be less than another small amount. I have to make one extra change here because I want x to be close to but not equal to 2. In other words, I want this distance to be positive. So I'll make sure that it's positive by making it bigger than 0. Okay, we're almost to the official definition, but let's look at an example. Suppose epsilon is 1. How small would I have to make delta? Well, in this case, I can look at a number line here. And on this number line, I'm going to plot the x-axis, and I'm going to look at 2 right here. Okay, so there is 2. And I want to know how small or how close to 2 I need to be so that f of x is, right here, f of x minus 4 is absolute valued is less than 1. Well, if it's less than 1, then that's looking at 3 and 5 here, right? Because the distance between f of x and 4 is less than 1, so it has to fall within this range. Okay, so let's kind of look at where this would be. So here's 3. If I kind of trace this over and trace it down, that should give me that value right there. And if I look at 5 and trace this over and trace it down here, if I keep going all the way down, that should give me that value right there. So what are these values? Well, I can figure this out. I know this function here. It looks like x squared at these two places here. So I can just calculate what these values would be. And it turns out that this one right here is 1.732, something like that. 1.732, that's this guy right here. And this one right here, if you calculate that one, it's 2.236. Okay. So I'm going to plot this on my number line here. So here's 2. 1.732 is somewhere over here, 1.732. And then 2.236 is somewhere over here. It's not to scale, I'm just kind of plotting it to get a sense of where they are. And now I want to look at the distance. How far away are they from 2? How far away do I need to be? Well, if I calculate the distance between 1.732 and 2, can do the difference of the absolute values of those, I get 0.268. So that's that distance right there. And then how about the distance between 2 and 2.236? So that's easy. That's going to be 0.236. So I see here that I have a distance of 0.268 here, 0.236 here. I'd like to pick just one value for delta and have a nice symmetric interval. So I'm going to take the smaller of these two. I'm going to take 0.236 and use that for my value of delta. So if I do that, then I see that if 0 is less than the absolute value of x minus 2, which is less than 0.236, that's my value of delta, then f of x minus 4, absolute valued, should be less than 1, and that's my value of epsilon. And any other value of delta smaller than 0.236 would also guarantee that I have f of x minus 4 absolute value less than 1. Like if I took something really, really close to 2, and I trace that back up, and I go over here, you can see that that would also guarantee that I am less than 1 unit away from 4. So this is the largest possible value, but anything smaller than that would work. Okay, I think it's time for the official definition here. So the limit as x approaches 2 of f of x equals 4 means for every epsilon bigger than 0, so any epsilon I can pick, and remember we're picking an epsilon that's going to be on the y-axis here. There exists a delta greater than 0, and that would be on the x-axis, such that if 0 is less than the absolute value of x minus 2, which is less than some small number delta, then the absolute value of f of x minus 4 is less than epsilon. In other words, if the distance between x and 2 is less than some small number delta, and it's greater than 0, then the distance between f of x and 4 will be less than some small number epsilon. So given an epsilon, I should be able to find a delta that works, and if that's possible for any choice of epsilon, it says for every epsilon, if it's possible to find a delta, then the limit as x approaches 2 of f of x must be 4. We can generalize this and say that the expression limit as x approaches a of f of x equals L means that for every epsilon greater than 0, there exists a delta greater than 0 such that if 0 is less than the absolute value of x minus a, which is less than delta, then the absolute value of f of x minus L is less than epsilon. And this is just a mathematical way of expressing this idea of a limit. So let's look at one more example. Suppose I have the function f of x equals sine of x, and I want to look at the limit as x approaches pi over 4 of sine of x. So I know that that's going to be the square root of 2 over 2. Here's a graph of sine of x, and so if we look at the graph, here is pi over 4, and I know if I were to trace this up and trace it over, that root 2 over 2 would be about here on the y-axis. Okay, suppose epsilon now is 0.01. What's the largest value of delta that would guarantee that the distance between sine of x and root 2 over 2 would be less than 0.01? Okay, so let's look at some approximations here. Root 2 over 2, that's about 0.707107, and pi over 4, that's about 0.785398. So I'm looking now on the graph at pi over 4, and tracing that up, and then right about here, so let's do that here. So if I trace this up and trace that over, that right about here would be root 2 over 2, which is about 0.707. That looks about right. And I want epsilon to be 0.01. That's a very small amount here. So I have a very, very narrow range nearby. So I'm looking at something that looks like this, where I just get these two values on either side here of what I'm looking for the limit. Okay, so this distance here is 0.01, this distance here is 0.01, and I want to know what these values are here. I want to know what this is, and I want to know what this is. Okay, well, I know that 0.707107 minus 0.01 is 0.697107, so that's this smaller value right here. So this one right here is 0.697. I'll just write that. And then I know that 0.707107 plus 0.01 is this guy here. So that's this upper value right here, and that would be 0.717. Okay. And now I need to figure out what these are down here. Well, this is the sine function. To figure out what these are, I can use inverse sine to get these two values. The inverse sine of the first value, 0.697, if I trace that back down here, do the inverse sine, so this is going to give me 0.771354. Okay? How about for this one? So for this one, if I do inverse sine, I end up getting 0.799. Let's write that down, 799643. All right, let's look at a number line here. So on my number line, I have in the middle pi over 4, which is 0.785398. And then on either side, I have two other numbers here. On this side, I have 0.771354. And on this side, I have 0.799643. And I want to know the distances here. So I can do the absolute value of these two things subtracted from each other. And if I look at this distance here, it's 0.014044. Just did that on a calculator here. And I look at the distance between these two, and I get 0.014245. And again, I want to take the smaller of these two and use that for my delta. So in this case, this one is the smaller one. So that's what I'm going to use for my delta. So if I pick delta to be 0.014044, then that will guarantee that the distance between sine of x and root 2 over 2 is less than 0.01.